Hello and welcome on today's video. My name is Wouter Pere and I'm the founder and main developer of geothermal Cloud. And in this video I'm going to share with you our major update on the interference module in geothermal. Now, the interference module was released in September last year. If you have not watched our video on this module, please go out and check it. It's linked in the description. But it has been gaining quite a lot of attraction ever since. And that's why we decided to update it to a major revision so that you can use this module now for every project you can imagine. So let's jump into this video. To recap, what's interference? Imagine you have a road, you have a district with a couple of geothermal systems already installed. And you ask yourself the question, okay, if I install a geothermal borehole myself, a bore field perhaps, how should I design it? Because every bore field, every borehole has a certain imbalance, probably. And this means that year after year, the ground will cool down, and this effect will also spread under the ground to our neighbors. So from the blue borehole here, what we can see is that it will make sure that our borehole, our ground, will be 0.5 degrees Celsius colder after a certain amount of years due to its presence and its imbalance. And this is the same for the orange or the red borehole here. And it will also have an effect on our system on the long term, as well as the pink one. So you can see that our system is in the middle of all these other projects, and therefore we need to take these projects into account in order to make sure that our system will stay within our limits, also taking into account our neighbors. And this was what we showed last time, so this is a real problem. This is an image from a situation in the Netherlands where a whole new neighborhood was built, and each house, each building has its own individual borehole. So of course all these systems they influence each other. And the way we could tackle this is by saying, okay, if we have a single borehole, it's easy, let's model it as a line. And we said, okay, you have finite line source and infinite line source, and the finite line source is actually more accurate than the infinite one. If you want more information, please check out our previous video. But the important thing is that we basically modeled every geothermal system as a single borehole. Now, what do we need to do when we have a bore field, when we have multiple boreholes in one geothermal system? Well, there we said, okay, let's model every bore field as a single borehole. So what we did is we say, okay, up to 6 boreholes, and you can say we have 6 boreholes. Let's take the geometric center and place a fictitious, virtual, let's say, borehole there to use for the interference calculation. Now, of course, this is not 100% accurate, but up to 6 boreholes, it was valid, according to literature. Now, this was the situation we had before. Now, we wanted to extend this to larger projects, because imagine the following situation. You have one project with residential buildings, apartments, divided in 3 different blocks. So each apartment building will have its own bore field located on the same project location, which you can see here. You have a rectangle bore field and then 2 other rectangles. And the question is, well, of course we know that these boreholes will also interact, these bore fields will also have an interference. But how do we calculate this? Because we cannot simply take, the geometric center of each, because that will not be accurate. And one approach could be to say, well, let's assume that the imbalance for each bore field is just equally divided across all boreholes. Then it would be easy, because then we know the imbalance of each borehole. But the problem is that not all boreholes in a certain bore field have an equal energy exchange with the ground. Now, to understand this, we need to think back about how the long-term effect of bore fields is being calculated. And this was with the help of these G functions. Now, if you have not watched a video on G functions, it's linked in the description. But conceptually, what we did is we calculated the interference between all the boreholes in the same bore field. And because this determines how the bore field reacts on a long term. And that we use to simulate the temperature profile. Now, if we would look a little bit closer to this G function, we know that not every borehole in the bore field has the same contribution to the overall thermal behavior of the system. And that is because imagine the boreholes in the center of the bore field. They have a harder time to get rid of their heat or their cold in the ground because they are surrounded by quite a lot of other systems. So if you simulate a bore field and you look at it very closely, it's actually the boreholes on the circumference, let's say, of your bore field that do the most part of the work. And the closer you are, or the more you go inside of your bore field, the less contribution your borehole will have to the overall behavior of your system. And this insight we can actually use to calculate the interference between larger bore fields more accurately. So what we did is we developed a new method and we said, okay, let's start with the calculation of the G function of the entire bore field, like we always do for all geothermal simulations. But then instead of stopping there, we take a step back and we see, okay, now we have this holistic approach of the thermal behavior of our system. Let's see what the contribution of each borehole was. And given this contribution, as you can see here again below, where the boreholes on the outer side of the bore field do the major work, we can use this contribution to scale the imbalance. So the boreholes on the outside will carry more of the imbalance and will get rid of more of the imbalance than the ones in the middle. And once we do that, we know exactly what the imbalance of each borehole in each bore field will be. And that we can use to calculate the interference between all the boreholes and then see, okay, what's now the interference between the different bore fields as well. Now this all sounds perhaps a little bit theoretical, so let's jump into GHGTool. I have prepared this project for you and let's see how easy it is to actually calculate the interference in real life. So here we are in GHGTool Cloud and I already created a project for us. So we have this residential project containing 3 different buildings, A, B, and C, each with a different bore field. So we designed already each bore field individually, yes. So we have here 32 boreholes of 73 meters deep, because there is a rock layer and we can't drill deeper than that. So we're limited to 73 meters. And you can see in the results that indeed all of different bore fields stay nicely within the limits. But this is of course looking at each system individually. So what you can now easily do is say, okay, let's duplicate our scenario and let's create a new one. And let's call this interference. Let's go to the calculate interference module. We are going to work with the generic calculation. Now in the Netherlands, there is a specific regulation using the seasonal performance factors for the system and the cooling. We're just going to use generic here because then we work with SUP heating and so forth. So that's minor detail. Let's work with the finite line source because it's a little bit more accurate. And to add systems, we're going to say we're not going to add a custom system. We're just going to say, well, link certain scenarios. So we're going to link building A, B, and C to this calculation. Let's say, okay. And now we're going to send this to the server and it will take the information for all our scenarios and calculate the interference with it. Now, as you can see, we have an error. Namely, there are duplicate boreholes in the bore field. Now, why is that? And that's one thing to keep in mind. If you are designing bore fields for each building individually, chances are that, as you can see here, we start at 0, 0, and then we have our geothermal bore field, and we have the same for all other buildings. So of course, if we now say, okay, let's calculate the interference, yeah, all boreholes overlap. So that's not ideal. So what we implemented to make your life a little bit easier are these functionalities to move your entire bore field to the location where you want it to be. So I know that my building B, it does not start at 0, 0. If I look at the whole project map, it actually starts at 60, 0. So what we can say is we can say, let's move the entire bore field. And from the old reference frame where it started at 0, 0, let's now start at 60 meters to the right. And what it will do, it will just move all the boreholes 60 meters to the right, and we can calculate it again. But of course it will have, yeah, the same temperature profile. It's now just moved to the right. As you can see here, still beautifully within the limits. Now, for our building C, perhaps you recall this only also needed to rotate at 90 degrees. So therefore we implemented a rotate bore field function. So let's say that we rotate around point 0, 0, and we're going to rotate our bore field with 90 degrees. So what this means is that our bore field at the location 0, 6, so that's actually this borehole, it needs to be over there. So we rotate everything. So we will rotate this until it's at 6, 0. So if we rotate this, we now have this rotated bore field, and let's move it also 20 meters down. And that's actually down, so that's here. And let's calculate it again. So what we now did is we said, okay, we have designed all our bore fields beautifully. We now move them to the locations where they actually are. And if we now again go to the interference calculation, press calculate again, it will take these real positions of the boreholes and calculate the interference. And here we are already. And what you can see, that is the interference table you're already familiar with. But you can see that our first bore field from building A, due to the existence of the other systems, will lower in temperature 0.8 degrees on the long term. So basically, if we designed here to be at a maximum of 2 degrees, a minimum of 2 degrees, we know that after 25 years we will be at 1.2 degrees, at 0.8 degrees lower due to the interference. And the same holds with building B and building C. And that's basically how easy it is to calculate the interference. Now, of course, this module is again compatible with your existent way of calculating interference. You can also import bigger systems if you're in the Netherlands from the WKO tool. It's all compatible. You can work with a CSV file and so forth. So you can import from a CSV from the WKO tool. It's really, really flexible. And basically there is now no limits to how you can, for which project you can calculate the interference. So I hope you found this video interesting. I hope you give this a try, because with systems becoming more and more complex, bigger, more and more collective systems, calculating the interference and getting this right is really, really important. So I hope this method helps you with that, and I'm looking forward to seeing you in our next video on our next innovation. Take care. Bye.